it flows down into the web. Okay, there is a direction. Whereas a terminal, okay, a terminal is where the shear flow has absolutely nowhere to go. Then we call it a what? A terminal. Terminal means end, right? Okay. So from here, what first moment of area to consider for point A, and what first moment of area to consider for point B. So for point A, the first moment of area we're going to consider is only up to here. Okay, so this is where it stops. I'm going to highlight. This is the first moment of area that we're going to consider. Looking at this, it's like a white flange. It's no more box beam. Okay. Whereas B, the area to consider, right? The area to consider is you have to consider this entire area over here relative to the closest what? Terminal. Yes or no? And it's going to be a box beam, right? So that's where we are going to focus to calculate our first moment of area. As you can observe by now, right? Calculating the first moment of area in thin wall analysis is so much dependent on your design of your shear flow. So from here, now you know, or we know what to consider in the first moment of area. So we are going to consider the box beam, sorry, point A. So let's consider point A. So we know point A, we are going to do white flange. And this is going to be Q. Okay. Another unique thing about this problem is a combination of what? Box beam and white flange, as you can observe from here. Okay. So it's why I like to write this, because it will remind me whether to divide by 2 or not to divide by 2. You don't have that, it can be pretty confusing. Right. So we know that this direction is the width. And this direction is the depth. Okay. So we know we are going to calculate our first moment of area about our z-axis with depth y bar. So width for this case is 2 inches. Our depth is 0.5. Y bar is 2.8362 minus by 0.5 divided by 2. So this will come out to be 2.8362 minus 0.5 divided by 2. Then 1.5 times 2 is equal to 2.5862. And this is in inches to power of 3. Okay, and then we're going to calculate the shear flow at point A. So By, so the formula we're going to use is By over Izz and Qz. Okay, multiply Qz. So By is 7 times 10 to the power 3. Qz 2.5862. Izz is 92.569. I'm just going to put a 1 down here. Okay, in exam time or term test, you don't need to write. This one is because it is white flange. Okay, for learning purposes, I just write it down. So it's equal to 195.567. inches to the power 3. Okay. Right. So the next one at point B, so it's straightforward. Okay. So the next one at point B, which we will consider. So at point B, we now know that the shear flow, by looking at the shear flow, right? The shear flow on the left, on the right web will come into T4, one terminal. So we know that this is our box beam. When that's the case, we have this as 2Q. Okay, so QZ is equal to width, depth, Y bar, and it's relative to the terminal, right? Because at the terminal is equal to 0, so the width is equal to so 6 plus 0.5 plus 0.7. The depth is 0.5. Now the Y bar, we have to be careful over here. Okay, so it's 6 plus by 0.5, which is the entire length, minus by the geometric centroid 2.8362, and then we minus by 0.5 divided by 2. Okay, this is how the geometry is taken. Okay, that's why I'm doing this. So from here, this will be 6 plus 0.5 minus 2.8362 minus 0.5 divided by 2 times by 0.5 times by 7. I get 11.9843. Inches to power 3. And I think I have a unit error over here. This is not inches to power 3. This is pounds per inch. Okay. So let me do the calculation again. Yep. So from here, we can calculate the Q at point B, right? So this is equal to Vy over Izz multiplied by Qz. So this will be equal to 7 times 10 to the power 3. And then we have 11.9843. And then divide by Izz, which is 92.569. And we have to divide by 2 because it's what? Box beam. So this will be equal to 7 power 3 times. So it's 453. Wait, 7 power 3 times. So I get 453 0.235 pounds per inch. Okay. And as you can see, the value is higher. It makes sense. And why I say it makes sense is because the area that we consider is bigger. Can you see that? The green portion, I mean, I did not draw in proportion, but if I'm going to highlight the green area, right, this region is so much more bigger, right, than the yellow region over here, as you can see. Okay, so the values does make a sort of sense. Now, the next part of this question, they want us to deal with the finding the maximum. Okay, we have to next determine the maximum shear flow. So the maximum shear flow, I'm going to do it also, is you can consider the top section and the bottom, and the answer should be the same. Okay, so I'm going to do it because it's been a week that I've not lectured you guys. I want you all to build up your confidence more than anything else. So the next part is we are going to determine the location of the maximum shear flow. Okay, so I'm going to take this diagram with us. Okay. So, and then I'm going to sketch a geometric centroid, right? And our geometric centroid, let me write this down. The y bar, which this value is important, is equal to what? 2.8362. Okay, from top. So we are going to consider the top section. So this is where I label this is our top. Wait, all of a sudden my pen don't want to write. So this is our top. And over here, this is our bottom, right? So again, everything is the same, right? Consider top, and we know that this is a box beam, right? It's going to be a box beam analysis. So it's B2Q. So we're going to do QZ. So it's a Q of the flange plus by Q of the web. Okay, so Q of the flange. So the width, so 6, 10, 11 for the flange, the width, the depth, and we have 2.8362 minus by 0.5 divided by 2. So this is for the flange. Okay, so let me check again. 6, 2 plus 2, 4, 10, 0.5 per side, 11. So that is 0.5, 2.8362 is the geometric centroid. The individual section centroid is minus 0.5 divided by 2. I think we are good. And then we're going to have a plus. The web, we have 2 web. The width is 0.5. The depth is 2.8362 minus by the thickness. And then, so this is the actual depth, and then we're going to take the actual depth, and then we're going to divide by 2. Okay. So this will be equal. You have to be really careful down here, okay? 2.8362 minus 0.5 divided by 2. Times by 11 times by 0.5. So it's, I'm going to write up the first one first, 14.224. All right, and then the next one is 2.8362 minus 0.5. I can square it times by 0.5 times 2 divided by 2. So it's 2.729. Okay, let me do the end. 2.83 69.5 squared times